Hi, everyone. Hold on one second. Let me just make, yes, okay. I just want to make sure I was unmuted. So today we're going to go over 2-4 scatter plots, correlation, and regression. Okay. So let's see what some of that means. So our key concept, we're going to introduce the analysis of paired sample data. So we have these two things that go together. For example, hold on. Okay, so for example, you could say, the older people get, the shorter they cut their hair. And that's paired data. Now, we don't know if that's true or false, but we want to let's say we want to see if that's possibly true. We would just have this question, and we could start doing some things that would give us some information. So we're going to discuss whether or not those two things are correlated. Like, is it true that the older you get, the shorter your hair gets? It may or may not be true. And the role of a graph called the scatter plot. So we're going to create scatter plots and provide an introduction to the use of the linear correlation coefficient. Okay, so we have a value that we can use that we can calculate. Also, we're going to provide a very brief discussion of linear regression, which involves the equation and graph of the straight line that best fits the sample paired data. So I'm going to pair data. So let's say, for example, I have here, I'm going to say this is age versus hair length. I'm sorry if you think this is a dumb example, but whatever it is, that's what I came up with. So let's say when kids are really little, like let's say they're less than 1, their hair is really short, right? Because it's still growing. And then, so let's put a dot there. And then, maybe they become 3, we haven't cut their hair, so it's growing a little more, and so on and so on. By the time they're 10, their hair is long, right? So this is the length of the hair. So it's getting longer and longer. But now at some point, who knows where, maybe out here when they're 40, they decide to get a new kind of hairstyle and they cut it really short. Okay, and they keep it short for a really long time. Do you see what I'm saying? So here we're trying to see if these paired data form any kind of a line, and it doesn't look like it. It looks like it's going to go up and maybe then it goes down. But we just made that data up, right? We have to actually start measuring. But that's basically what we're talking about. Okay, let me get rid of this. Okay, so a scatter plot and correlation. So a correlation exists between two variables. We just talked about two different variables, age and hair length. When the values of one variable, so we graphed age at the bottom horizontally, and we graphed hair length vertically. So if we were to do that graph, I guess I'm just going to keep carrying it through now that I started it, right? Okay, so there's my two values, and if you remember from algebra, you may or may not, this is the x-axis and this is the y-axis. So that's what we're talking about. We have two variables. We'll call them x and y, but here we can call them age and hair length. So we're trying to find if a correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. So are they associated? We don't know. So here's one thing to be cautious about. The presence of a correlation. Here, let me make this smaller over on this side. Gives me a little more space here. So the presence of a correlation between two variables is not evidence that one of the variables causes the other. We might find a correlation between beer consumption and weight. Maybe that would have been a better example. But we cannot conclude from the statistical evidence that drinking beer has a direct effect on weight. Correlation, this is very important right here. Correlation does not imply causality, because many things could have happened. You could have started drinking beer and at the same time stopped exercising and maybe started eating bad. So what was it? Was it the beer consumption? Even though your weight went up as you started consuming more and more beer, there's other factors that we haven't taken into consideration. So we can't say that it actually makes something happen, okay? So, here, let me get rid of this. Hopefully I don't need it anymore. Okay, and it says a linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So I'm going to show you pictures. Don't worry, I'll show you exactly what that means. So we're going to talk about a scatter plot and correlation. So a scatter plot, or sometimes we call it a scatter diagram, is a plot of paired XY quantitative. We talked about quantitative in one of the first few lectures. That means numeric, right? Data. And they're saying that we have a horizontal or x-axis and a vertical y-axis, just like we always would talk about. So we would have a horizontal. So this is horizontal. This would be the x-axis. And a vertical, this would be the y-axis. Okay, and that's how we would graph things. So for example, if we had a bunch of values, and I'm going to do this for you, don't worry. If we had a bunch of values and we plotted each one, notice we're not putting lines or we're not connecting them, we're just plotting dots from where these points are. So we can kind of see that in general, as the waist circumference increases, so does the arm circumference. Sometimes not as much, sometimes more, but we can see that there is a distinct pattern of the plotted points, and it suggests that there is a correlation between waist circumference and arm circumference. We can see it's kind of going, take a stab at it. So let's say it's kind of following that line, right? Now we're going to look at another one. This one is weight and pulse rate. So we have weight on the x-axis and pulse rate on the y-axis. And like, if I pick a point, as I go, as my weight goes up, does my pulse rate go up? Well, not necessarily, because let me see. Here's a high pulse rate with a smaller weight, and here's a smaller pulse rate with a bigger weight. So it doesn't seem to be going exactly in any direction. It kind of is just spread everywhere, right? And so the plotted points do not show a distinct pattern. So it appears that there is no correlation between weight and pulse rates. Okay. Yeah, I'm going to continue for just one more second, and then I'm going to do an example. So linear correlation coefficient. Actually, let's stop here. Let me do an example. So I'm going to go to a problem. This is a problem that I picked from Pearson. It is not a problem in your homework, but it is similar. And I wanted to show you how to use StatCrunch, because we could plot all these points. We can see here that we're plotting tar on the, let me see if I can write on it, hold on. So we can see here we're plotting tar versus carbon monoxide, okay? Sorry about that. And, okay, so let's see. But the problem is I don't want to I don't want to plot every one of these points, right? So what I can do is, if you look up here in the upper right-hand corner, there's this little box and it says click to copy table. So I'm going to click it and it says open in StatCrunch. That's what I want to do. I want to open it in StatCrunch. And when I do that, all the data from this table here, notice, here's my data, 16. So my first line is 16 for tar and 15 for carbon monoxide. And I have 16 for tar and 15 for carbon monoxide. So I'm not going to go through all the points, but you get the point. You can do this without using StatCrunch, but I'm going to use StatCrunch because I think it will make it a little easier. So I'm going to go up here and I'm going to graph a scatter plot. And my x-axis, we can see, is tar. So let's pick tar. And my y-axis is carbon monoxide. And I don't think there's anything else I really want to put here. No, I'm good. And then I hit compute. And there is my graph. So let's look at A. We can see pretty clearly that it isn't A, right? So how can we tell? And let me, hold on one second, let me fix this. So I can come over here and I don't even have to make it bigger. I can see that here we're starting high. We're starting up here and we're kind of coming down, right? Like the bigger tar gets, the smaller the carbon monoxide gets. But that's not true with the graph that we have here. So I'm going to say, no, it's not that one. Okay. Let's see what else we have here. We have B. It's so not B, right? Because B is just going all over the place. I don't have any kind of pattern that looks like B. So let's cancel B away. Now, C and D both have possibilities. So how can we tell? Well, we can look at certain identifiers, like we have this one point out here, which they both have that, right? But notice these points right here and these points right here, those are going kind of up and down, and these are going side. So these are going side to side and these are going up and down. So I'm going to guess it's D, but we can even do a little better than that. So here, let's clear all my drawings and we can open this up. So we can just click this open, more as big as we want, really. And let's go back and get our plot. And yeah, it's exactly like we saw it when it was small. These dots don't match. This doesn't really seem to match very well, right? It kind of starts out well and then it kind of goes off. So let's look at this. And another thing I can do, instead of making things bigger and smaller, I can do this, which just pulls it completely out. And it makes it pretty much as big as it'll get. So let's look at these next to each other. Okay, so there's my same 2 points. And then see these 2 points right here? This one right here, these are horizontal and we have the same ones here. Everything looks exactly identical, right? Can you see that these are identical? So that means my answer is D. And I don't really have to do much more than that to say it. I just want to show you how you can use StatCrunch instead of plotting points. Okay. So let's go back to our PowerPoint. And now we're going to talk about a linear correlation coefficient. So this linear correlation coefficient is sometimes called small r, and you'll see sometimes it's called big R. Doesn't make a difference. They mean the same thing. And it's denoted by small or large r. And it measures the strength of the linear association between two variables, how much they form a line, basically. Linear meaning line. Think of linear as line, okay? So using R for determining correlation. The computed value of the linear correlation coefficient R is always between -1 and +1. If R is close to -1 or close to +1, there appears to be a correlation. So let me show you what that means. Notice, let me see if I can make this a little bigger. I'll make this like this. So notice how straight this line is. It looks like if I have a lot of points, I can hardly tell, right? Because they're all lined up very much in a line. And that line, if I were to, I always read from left to right, right? I always read from left to right. So when I read this from left to right, we can see that it's increasing, right? It's starting small and getting bigger as it goes. So when it does that, it has a positive correlation. Now, I can still see that this is a line going up. They're not, the points are scattered a little more around that line, but I can still tell there's a line. And 0.8 says it's still pretty good, right? Now notice at 0.4, it's getting harder to tell. We know it's not going down, but you can almost tell it's increasing, but it is getting harder and it's got a very small r. And this one, 0, you can't tell anything. It just looks like it's going around in a circle, right? And then again, -0.4, if this is going up, this is coming down, but it's not very distinct, which is why it has a small r number. So when I talk about r, let's talk about the absolute value of r, or just if it was positive. If it was positive, and remember the absolute value has to be between 1 and 0. And it could be 1 and it could be 0. This means absolute value, and it just means make it positive. Okay, so this means absolute value. And it means, it actually means distance, but it's just always positive. That's a good way to think about it. Okay. So even if my R is negative, it's still, I put the absolute value around and I say, okay, let's make it positive. It's going to be somewhere between 0 and 1. That's basically what that means. So these two numbers, the absolute value of them, are still very small numbers. They're very close to 0. Now, I know this looks like it's a smaller number, but it's not, because we're talking about the absolute value. It's just the negative just means instead of going up, the line is going down if I read it from left to right. Right, this is going up and this is going down, which gives me a negative value. And then we have this one here, which is a very nice line. Okay. Okay, so another thing to think about is so imagine that I put this on an XY axis, right? Let's say this is X and this is Y. We can see that as X increases, Y increases, right? And that's true everywhere, here, here. It's not really true here though, right? As X increases, Y doesn't change. So there really is no correlation because X can do anything and Y just stays the same. So it's really it has no correlation. This would actually be 0. Even though it's a straight line, like as one thing changes, the other one does nothing. So they can't have anything to do with each other, right? It's like saying, if I guess I'm going to do hair again. So if I cut my hair, your hair doesn't get shorter, right? So there's no correlation between me cutting my hair and you cutting your hair. So we could have a line that's straight, but there's no correlation between them. And then notice as we go to negative, as X increases, so X here is increasing, the Y value is decreasing. That's what gives us our -1. And it doesn't matter how much of a slope there is. It only matters that it's going down. As X increases, Y decreases for negative, and as X increases, Y increases for positive. All right, let me make this back to a little bit smaller. And I will erase all that. And then, so we talked about that. Now we can see that here, there is no linear correlation, right? There's no lines that make this all true. So these are zeros. They form some nice pictures, but here's a circle. As X gets bigger, so if I were to put this on a graph, right? Here, as X gets bigger, Y gets bigger, and then all of a sudden, but we also have the top part, which says as X gets bigger, Y gets bigger. I guess for both sides, as X gets bigger, Y gets bigger. That's true, but it doesn't matter. It's still 0. It's not linear. I mean, that's the best I can offer you. It is not linear. Okay, so next, let's talk about this next slide, and then we're going to do the next problem. So how do we find out something about correlation? So actually, let's do the problem. Well, no, let's do this first. So if something is correlated, so if the computed linear correlation coefficient R lies in the left or right tail region beyond the table value for that tail, conclude there is sufficient evidence to support the claim of linear correlation. Let me break that down for you into English. So let's say I talk to 10 people. So I have 10 pairs of data. That means I have a critical value for my R of 0.62. Okay, I'm going to come off of this graph. I'm just going to draw it up here. So this is 0. This is 0.62. I'm sorry, 0.632. And here we have negative 0.632. Because remember, we can go from -1 to +1. And the value that it's giving me here is just the positive. There's always going to be a positive and negative critical value. And my critical values are right here, critical value, and right here, critical value. Okay? If my R is between those two critical values, we can see that there is no correlation. Okay? That means it could just happen it could happen randomly. There are things that happen randomly that are like a coincidence. We do have things that are called coincidences. And even though not everybody believes that things are a coincidence, I would say that there's a good chance that there are some things that are coincidental, right? So what we're saying is that if it's between here and here, consider it like it could be a coincidence. It could not be a coincidence, but we don't really have enough data to tell. Okay, that's basically what it's saying. If it lies outside of the critical values here and here, this means that we do have a correlation. We probably have a correlation. So this is correlated, and this is correlated. That's what this graph is saying. So if the R value is bigger than positive 0.632 or smaller than negative 0.632, then we can say we do have sufficient evidence to support the claim of a linear correlation. If it's in the middle, here and here, right, then we conclude there is not sufficient evidence to support the claim of linear correlation. Okay, so let's see what that means. So let's say, for example, we have these 5 data points, okay? And I'm going to do this for you. I can do this for you in StatCrunch, so I think I will. So the first thing I'm going to do is notice StatCrunch can stay open even when I'm not on my program. It's kind of separate. So I'm going to close this down, and I have a bunch of data sets in our, let me see, where do I want to go? Maybe here. Nope. Oh, and I'm sorry, I did not even finish this problem. I guess I should finish it. It says, is there a relationship between cigarette tar and carbon monoxide? And we picked D, and I'm going to say, yes, it looks like there's a straight line going up. So it says, yes, as the amount of tar increases, the amount of carbon monoxide decreases. No, that's not true. They're both increasing, right? So that would be B. So A would be, so this answer, yes, the amount of tar increases, the amount of carbon monoxide decreases, that would go with graph A. And no, there appears to be no relation. We could say that if we had picked graph B. Graph B does not look like it has any correlation. Okay, so that's not what I meant to do, but why not? And we're going to save this next problem. Let's save this problem for a minute, because I was going to do something else. Okay, so I'm going to go back to my class. I know none of these are well, at this moment, none of them are published for you, but by the time you see this, this will be published. So I can go here and I can go to files. This is the Canvas course. And here we see Excel data sets. And there's our Excel data sets. And we're going to pull up this foot and height Excel spreadsheet. Okay. And I'm going to download it. All right. And close it. And then I'm going to go back to StatCrunch. And let me close this down. Let me close this down. Yeah, this is where actually where I wanted to be was here and StatCrunch. So what I want to do is I want to get these 5 data points. And I actually have a spreadsheet with those 5 data points, I believe. I should anyway. Let's see. Let's see, 5 points. Do I have it? Nope. Those are not 5 points. Let's see if I just mislabeled it. Otherwise, I'll go get them back anyway. We can even just type them in here. Probably faster to just type them in. Okay, so this is going to be shoe print length. And this is height. And let me get rid of all of this. I don't know how far down that goes. Oh, so it goes further. Okay. Yeah, that's it. All right. So first point is my X is going to be 29.7. I'm just going to put them all in a row, 29.7, 31.4. Oh, I can't. Never mind. I can't do that. Height is 175.3. I have 29.7 and height is 177.8. I have 31.4 and that goes with 185.4. I actually lost one. Okay, that's not good. 29.7, 177.8, 31.4, 180. Okay, that's right. 31.8, 31.8, and 175.3. And last, 27.6 and 172.7. Okay, I mean, it's just as easy to do it that way. Now, I want to know, first I want to do our plot. So I'm going to go here to graph, scatter plot. And my X value is going to be shoe print length, and my Y value is going to be height. And that's really all I need. I'm going to hit compute. And let's see, I'll make this bigger. And it's a little smaller. I want to get them on the page at the same time. So, that's pretty good. So we can see that this looks exactly the same. These points are the points in my graph. So, for example, hold on. Back over there. Okay. All right, so if I want to find this point, So my X value is 29.7, close to 30, and 175.3. So this point right here looks like it's going to be 29.7, comma 175.3. And notice we have another 29.7, so that must be this one right above it, right? So that point is 29.7, comma 177.8. So, 5 points you could actually do by hand and so on. And that's really what's happening. That's how I'm getting this scatter point, this scatter plot. Okay. So let's close this and we will erase that. And let's go back to our PowerPoint. So there it is. I have my scatter plot. It kind of looks like maybe it's going up. Like these points are going up, these points are going kind of sideways. Maybe we could draw a line right through the middle of the two of them, like maybe here. Who knows, maybe here. We don't have really a lot of data points. It's very hard to draw a line. You don't have really enough data, okay? But we can do it. Next, it isn't, as I just said, it's not really very clear whether there is a linear correlation. So here we can see, and I'll show you how to get this from StatCrunch as well, that here my R is 0.591269. So let's say 0.59, right? Well, it's not that close to 1. It's not really very big, but let's see what it looks. Let's see how we get that from StatCrunch, because part of the point here is to actually get the data. Let's open up. So I'm gonna grab, probably have them mixed up. Let's see. Yeah, I had them mixed up. All right. So I have, okay, so here's the original, and I want shoe print. So I'm going to get rid of all this. And these are things I can always check see if anything's between those two. But it was shoe print and shoe and height, right? That's the two things we were looking for. So I am going to copy. So you don't have to do this. I'm just showing you what I'm doing. Okay. So I'm gonna paste them in here. Try one more time. Paste them in here. Are you gonna let me? Hold on. Maybe not. Oh, you grab it again. Oh, okay. I guess I closed it. Sorry, guys. Should be this. Okay. Let me do this. So this has 40 points. Okay, so I'm going to copy it. And I'm going to go back to StatCrunch. And let's see if I can paste it in there. There we go. Exactly what I wanted. Okay, so now I have the 40 points that were in the original file. And I didn't take it just 5 points out. Okay. And we want to see, does anything change here? So let's do the graph. So I can do a scatter plot. We know shoe print, height. And let's compute. So there's my scatter plot. It's still going up, right? And I can also go here and go into regression, simple linear. And I'm going to pick X is shoe print, Y is height. And that's I think all I need. And that's how I get my table that has all the information in it that tells me about my graph. Okay, so here, notice my correlation coefficient has changed quite a bit. It was 0.59, I believe. Now it's 0.81. That's a lot better, right? So let's go back and see. This was with 5 points is 0.59. And we're going to talk about this in a minute. Actually, I'm going to talk about it later. I'm not going to talk about it now. So we don't really know much about it, but we can also look at our P numbers, okay? So p-value. The p-value is used to measure the significance of the observational data. So when we identify an apparent relationship between two variables, so let's say we think there's a relationship between shoe print length and height, right? So that's what we say. Sorry. There is always a possibility that this correlation might be a coincidence, right? The p-value helps determine if the observed relationship could arise as a result of chance. The larger the p-value, the more likely it could arise by chance. So to be sure that we're using data that actually is real and makes a difference and is not just happening by chance, we want the p-value to be below 5%, which is the same as 0.05. So basically, if you have percent and you want to go to a decimal value, 5% means 5/100. So I can also say this is 1/20. But what I really want is my decimal, and 5/100ths is the same as 0.05. So how do we get from there to there? I start with my 5%. I want to divide by 100. Every time and I know that it's going to be smaller than 5, right? If I divide 5 by 100, it's going to get smaller. Every time I move my decimal place one place to the left, it gets smaller by a factor of 10, right? So 0.5 is 5 divided by 10. If I move it again, that's 5 divided by 100. And inside here, I put my decimal place, my 0. And I can put a 0 out here. So we get 0.05, which is exactly the same. So that's a really nice, easy way to do it. Just move your decimal place, okay? So if my p-value is below 5% or 0.05, that means it is unlikely to be arising by chance, okay? Well, let's see what we have here. This is the p-value, by the way. In this chart, this is the p-value that we're talking about, is this slope. And that is definitely bigger than 0.05 or 5%. That's actually 29.37%, which is very high, right? So because of that, we really don't know if there is a correlation. So interpreting a p-value from the previous example, the p-value of 0.294 is high. It shows there is a chance of getting a linear correlation coefficient of R equals 0.591 or more extreme, meaning it could be even a bigger R by chance. Okay, so because this p-value is so high, and I highlighted it in both places, because this p-value is so high, that's a pretty high chance, almost 30% chance that it just happens by, it just happens. It's not, it didn't happen because they really affected each other. So let's see where I am. or more by chance, even though there is no linear correlation between the two variables. So that p-value is too high. But if we go to the one where we had 40 points, let's see if I still have it open. I do. So notice this one, I have 40 points. And look at my p-value. It's way less than 0.05. So 0.05, and this is way less. So 0.05 is greater than 0.0. How many zeros? I have 3 zeros. So we know that's true, which means that it's very unlikely that this happened by chance. And look at my correlation coefficient. It got bigger, didn't it? So it got bigger, meaning it seemed to actually become more linear. And my p-value is very small, which means there's a very low chance that it happened by accident. And so now we've really talked about a lot of different things that are happening. And we've learned how to use StatCrunch, which is actually very important. Erase this stuff. All right. And then we talked about this. Let's see. Okay, so interpreting a p-value from the example where n equals 5, because the likelihood of getting r equals 0.591 or a more extreme value is so high, it's at 29.4% chance, we conclude there is not sufficient evidence to conclude there is a linear correlation between shoe print length and heights, okay? So if I went back to here, right, I had 5 pieces of data for the one that I used. So I would come here to 5 and I would say, okay, so my critical values are 0.878 and negative 0.878. Let's put 0 here in the middle. And my value, my R value was 0.59, which is between my critical values. And when they're between the critical values, as we can see, there's no correlation. Okay, let's see, where are we at? I think we did that. Yeah, we were just talking about this. We saw this information. We just talked about this. So here, because our p-value is so small, just like I just said, we have sufficient evidence to conclude there is a linear correlation between shoe print length and height. Okay, so let's do another problem from the homework, because now we have enough information to do this problem. And it says for a data set of brain volumes, centimeter cubed, and IQ scores of 8 males. So 8, that seems important, right? The linear correlation coefficient is R equals 0.277, which seems kind of small to me, right? Use the table available below to find the critical value of R. So there's my table. And I have, so let me highlight what I have. I have 8 pairs of data. 8 pairs of data. So I come over here. I have my number line. I have 0.707. Let's make this 0, negative 0.707. Okay, we always have the plus and minus. And my R is actually right around here, 0.8. 0.277. So what did we just say about the critical points? These are my critical values. And when R is between those critical values, what do we say? We say that first we put in the critical value. So we put in either 0.707, you could just put in 707, it doesn't matter. You can put in plus here, and then you can put a comma and minus, or you can use this little plus minus, which means I want the positive and the negative of that value. Either way, whatever you like best. And that's perfect. All right, since the correlation coefficient R, so we know that's 0.277 and we put it on our graph, is between the critical values, there is not sufficient evidence to support the claim of a linear correlation. Remember, no correlation between the two values. And there we have it, okay? So let's see what else we're gonna do. I have one more example so that I wanna fit it into the right place. Okay, so we did this. Okay, good, let's talk about regression. So given a collection of paired data samples, now we know what that means. The regression line, which is the same as the line of best fit. So what line fits the data the best, or the least squares line? The least squares line basically means that I'm finding the distance between my point and the line that I'm assuming it is, and I'm squaring it, which makes it positive, right? So now I add up a bunch of positive values. And whichever has the smallest value would be the line of best fit, which we would call the regression line. And it's the straight line that best fits the scatter plot of the data, okay? So the regression equation is here. And I know that looks weird, right? But we've all taken algebra. You may or may not remember algebra, but maybe this will help. The equation of a line in slope-intercept form would be y equals mx plus b. That's just where m is the slope. Remember, m is the slope and b is the y-intercept. B is the y-intercept, which means where the graph hits the y-axis, okay? So we call this y hat because we're kind of approximating. It's not an actual definite value. And all I'm doing here is I'm saying, I'm taking y and making it y hat, and I'm changing the order of these two values. So I'm going to put b first, plus mx. And this b refers to this b. This is the y-intercept. If I were to look on a graph, let's say we have a graph that looks like this, except I wanted to start it here. Let's say we have a graph that looks like this. This is my y-intercept, okay? So that's like where I start. And B0 means exactly the same thing, where this line starts. And then B1 is our slope, okay? And then we're gonna multiply by x. It's exactly the equation of a line. So don't get confused by this. So we have this regression line, okay? And we can create this. Let's go back to our stat crunch. And I think this is the one with 40 points. So I think that's the one we're using right now. And actually, let's close this. And we'll put this here. Let's try this. Okay, actually, I closed the wrong one. Let's move this down. And let's go back and graph that one. Let's graph the scatter plot, shoe print, height, and we're gonna overlay a polynomial of order 1. What that means is it's a line. Order 1 means 1 degree. So x to the first power. If you wanted it to be 2, it would be x squared, but that's no longer a line. That would be a parabola. We don't want parabolas. We want polynomials that are lines. Okay, so we say 1. And I believe that's really all I need to do. So let's compute. And we have a graph. I'm sure that if I stretched it the way they stretched it. Okay, so that looks pretty close, right? And if I hover over this line, notice I have an equation, okay? You see? Where does that equation come from? Did I do that again? I think I might, okay. Should have kept them both. Okay, so notice, okay, here we go. I got another thing to look at. So here's my line with the numbers. And notice those are the same numbers, hold on, as so here's our intercept and here's our slope. And let me go back and hover again. Go with my name. Okay, here we go. So there we have it. There's our intercept and our slope. And they're saying that the height, which is our y, right? There's our y, is equal to that the 80.93 plus the 3.21 times, we said times x, they said times shoe print. Our shoe print is our x, right? So let's see. Do we want anything else from here? I don't think so. Nope. And just like I just showed you, and oh, I didn't show you this part. Let me show you this part because I made it really small. So if I open this up and I open this up, notice, excuse me. So we have our parameters. There's my intercept. So remember we said y equals mx plus b. Y equals mx plus b, where m is the slope and b is the y-intercept. So we're using y hat is equal to the slope. Well, here's the slope right here. 3.22. I'm just going to round it to 2 decimal places times x plus our intercept, 80.93. And if I want to put it into the form that they would like, it's 80.93 plus 3.22x. These are exactly the same. I just changed the order. And look at our p-value. Our p-value is tiny. What is that? What does a tiny p-value mean? And we only look at the p-value for the slope. And you can use this p-value. These p-values will match. The intercept p-value don't use. So this is telling me I have a good estimate, isn't it? Like this line should represent points along the graph. Okay, points maybe that I don't have, I can fill in. Okay, let's go back to our slides. Okay, so the general form of the regression equation has a y-intercept of 80.9. Okay, they rounded it a little more than I did, and a slope of 3.22. There are the values, and we have our, let me get, I can do here. So we have intercept, slope, notice, small p-value, and here, this is basically right here, right? And we can write the equation of the regression line as y hat equals 80.9 plus 3.22x. And that's really it. I mean, really, StatCrunch does most of the work for us, right? And that is actually the end. I do have one more problem though, so let's do that now. Okay, so it says because I really want to show you StatCrunch as well. So for a data set of weight in pounds and highway fuel consumption amounts of 10 types of automobiles, so there's our 10. Will we need it? We don't know. The linear correlation coefficient is found. They're not telling us what it is, but they are telling us the p-value is 0.012. So our p-value is 0.012, okay? And I want to put that in here as a percent. So I have to multiply by 100. Remember when I went from a decimal, when I went from a percent to a decimal, I started with a percent and I went to a decimal by moving my decimal place 2 places to the left or dividing by 100. So if I want to go from a decimal to a percent, I multiply by 100, which is really the same as moving this decimal point. This is times 10 times 100. So this equals 1.2%. Okay. So I'm going to put in here 1.2, which is low, right? It's under 5%. When it's under 5%, there is sufficient evidence to conclude that there's a linear correlation between weight and highway fuel consumption in automobiles. If this was above 5%, it would be high-ish. I mean, if it was 6, I mean, you may not call it high, but it's high enough that there would not be sufficient evidence to conclude that there's a linear relationship. And let's check our answer. We did it. And that concludes this video of 2.4. I think I've gotten everything you need. If you have any questions, please feel free to reach out. I do have office hours. I will always announce them. They're in the syllabus. And I don't want to say it on the video because I might change them, but they'll always be there. And if those don't work for you, just send me an email and say, I'm really having a hard time understanding exactly what you said, what you meant by this. And I could maybe explain it. Maybe we could do a Zoom call, just you and I, or we'll figure something out. You can also go ask the TAs. We have a TA for each class. So there will be, I'll give you the schedule of how you can get a TA. If you're fully online, we do have fully online TAs. So don't worry, reach out, don't disappear. If you disappear, it's much harder to help you than if you reach out. All you have to do is reach your hand out. I promise I'm going to catch you. Okay? So this is it until next time. Thanks for watching.